minutes. Is it visible?
Yes,
Yes,
ma'am.
ma'am.
Okay. We have started with Unit 2 in last week, and we have discussed about how to calculate the design parameters for rectangular RC section. We learned about three design parameters, or which are also called as design constants. Can you quickly tell me the values of the design constants? The first one is, yes, anybody from you?
Neutral axis factor. Neutral axis factor.
It is denoted by
Ku max.
Ku max, okay. And the formula?
700 by 1100 plus 0.87 Fy.
Okay, correct. Next, second,
RU max
okay.
equals to 0.36 FCK into KU max into bracket 1 minus 0.42 KU max bracket 20.
Correct, correct. The third one,
Percentage steel factor.
yes,
And that is 0.36 FCK Ku max by 0.87 Fy.
into 100. Last time
Yeah, ma'am. Yes,
I
ma'am.
added it later on. So it is a percentage steel, right?
Yeah, ma'am.
So multiplied by 100. Okay, correct. So these are the three design constants, and we have also solved two numerical examples, or not two, actually, rather, we have prepared a table by considering the various grades of concrete and various steel grades, Fe250 and Fe415, and we have created a table for all these three design constants. Today we will see the next point, that is how we can calculate the moment of resistance of rectangular singly RC section. So this diagram you are well aware. It shows a cross-sectional view of a beam. This particular beam in which the reinforcing steel is provided in tension zone only, it is called as singly reinforced beam. Okay, there are three types of reinforced beams. One is singly reinforced, second is doubly reinforced, and third is the flanged section. Okay, so we will study today about the singly reinforced section. The beam in which the steel is provided in tension zone only, it is called as singly reinforced section. So this is a beam having width B and the effective depth of D, with the depth of neutral axis indicated by XU. This is the strain diagram and this is the stress diagram. Last week or in the previous lecture, we have discussed the same diagram and we have checked the values for the balance section. Okay, and for balance section, we have calculated the design constant. Today, we will see the under reinforced section. Now, if for under reinforced section, these are the values for various parameters considering your beam cross section, the strain values, and the stress values. So, quickly, anybody tell me, please, what do you understand by under reinforced section?
Percentage of steel is less than the concrete means before the steel fails and then the concrete fails in this part.
Concept is clear, but the definition is little wrong. Percentage of steel is less than the critical percentage steel. You have to always discuss or define the types of sections with respect to the percentage of steel in comparison with the percentage of steel provided in balance section. The percentage of steel provided in balance section is called as critical percentage steel. Okay, so we always define the types of beams based on the critical percentage steel. So under reinforced sections are those in which the percentage of steel are less than the critical percentage steel. Ultimately, what you have discussed that the percentage of steel or amount of steel provided is less than the amount of concrete. This is not the truth. Actually, the percentage of steel is less than the critical percentage steel, and because of that, the steel reached to its maximum strain value first rather than concrete. We cannot compare the quantity of concrete with quantity of steel. Huh? Keep this always in mind. We never say that the concrete is more than steel and steel is more than concrete. Is it clear?
Yes, ma'am.
Yes, ma'am.
Okay. So for under reinforced section, the percentage of steel is less than the critical percentage steel, and hence the XU value, that is the depth of neutral axis, always come less than the XU max. Now XU max is nothing but the depth of the neutral axis for balanced section. Now, though in this section, the steel reached to its strain value, maximum strain value, to its yield point first, the criteria for failure is always considered as the failure of concrete. So we further allow the section to carry the load, and we consider the point of failure only when the concrete reach to its maximum strain value. So here also the epsilon c is considered to reach to the ultimate value, which is equal to 0.0035. Now as the steel has started yielding first, obviously the strain in steel goes on increasing when we further load the section. So at the time of failure, the epsilon s, that is the strain in steel, is always greater than epsilon sy, that is the ultimate strain of the steel, which is given by this formula, and both these formulas or values are defined by IS code itself. Rather, we have discussed how these values are obtained in this section. So in the under reinforced section, the force of compression Cu is calculated by using this formula, that is 0.36 FCK B into XU, average stress into area, and force of tension Tu is calculated by this formula, again the average stress into area of the steel, 0.87 Fy into AST. So these are the values for the under reinforced section. Do you want to write down this somewhere in your notebook? Because we'll require all these values
Yes, ma'am.
for the numerical examples. So just note down these values for under reinforced section. XU is less than XU max. Rather, this is the criteria based on which we can identify the type of section. If your XU is coming exactly equal to XU max, we call that as a balanced section. When XU is coming less than XU max, we identify the section as under reinforced. And when XU is greater than XU max, we identify the section as over reinforced section. So to calculate the XU value now, we require all these values or the constants. These are not actually the constant, these are the parameters. Epsilon Cu, epsilon S, force of compression and force of tension. We need to calculate all these parameters. Have you written down this?
I'm doing 2 minutes.
Okay. Once you finish, please let me know, then so that I can proceed to the next slide.
Then, ma'am. Yeah.
Okay. Okay. Now, as we have discussed, these are the parameters for under reinforced section. And to find out the values, various values, specifically the moment of resistance for under reinforced section, we have to consider first the depth of neutral axis. That is, we have to locate the depth of the neutral axis. For that, we have to equate the total tensile force to the total compressive force. So Tu is equal to Cu. So we have 0.87 Fy into AST as a Tu value and Cu 0.36 FCK B into XU. Equating this, we can find out the XU value. So XU is equal to 0.87 AST Fy upon 0.36 FCK B. By making use of this formula, we have to calculate now XU value for the given cross section of a beam. Further, we have to compare this XU value with the maximum XU value. XU max value we can calculate by making use of the design constant. We already know the relation between XU max and KU max, that XU max is equal to KU max into D, right? So by using that formula, we can find out KU max. then we can find out XU max, and then we can calculate XU by making use of this formula and compare it with XU max. If the value is coming less than XU max, it is called as under reinforced beam. If not, then it is called as over reinforced beam. Now, once you know the depth of the location, the location of the depth of the neutral axis and the type of the beam, we can easily find out the ultimate moment of resistance of the section, which is calculated as MUR equal to CU into ZU or TU into ZU. That is the force of compression into lever arm or force of tension into lever arm. So the formulas are ultimately this. MUR is equal to 0.36 FCK B XU into bracket D minus 0.42 XU. This one is your CU and this is ZU, or this is TU and this is ZU. 0.87 FYAST into bracket D minus 0.42 XU. Any one formula you can use for calculation of ultimate moment of resistance for under reinforced section. So all of you just note down all these, the derivation, especially the XU formula and MUR formulas. This is required for solving the problems further. Are you writing?
Yes, ma'am.
Okay. Once you complete, please let me know. Just note down the formulas. The detailed derivation you can get because I'm uploading all the notes on VOLP. Have you joined VOLP?
Yes, ma'am.
Okay, so on Friday I have checked that around 48 students have joined the VOLP course of SDD1. What about the others? Is there any problem for joining VOLP? Because the next assignment, the next test, everything I'm going to share on VOLP only. So it is necessary that everybody have got the access to VOLP. Is it over? Guys?
Yes, ma'am. Done.
Okay, fine. So this is the formula for calculation of moment of resistance for under reinforced section. Let us see the over reinforced section. Now the diagrams for the cross section of beam, strain diagram and stress diagram will remain same. Only the values here will change. In case of over reinforced, what happens? Can you define me again the over reinforced section?
When in the over-enforced section, when the load comes, when first the concrete strain reaches to its maximum value, that is 0.0035, but yet the steel has not reached its yield point, and therefore the structure collapses.
Okay, this phenomenon you have explained, but you have not defined over reinforced yet. How to
Section
define over?
percentage of
And
steel
steel is
is
more than
greater than
its critical percentage.
Correct, correct. Both of you have given the correct answer. The section in which the percentage of steel is greater than the critical steel percentage is called as over reinforced. And in this section, the concrete reached to its ultimate strain first, that is the value of 0.0035. And as the concrete is brittle, it collapses suddenly. So the strain developed in steel is normally or always it is less than the yield strain value, that is epsilon SY. Okay, so for over reinforced section, these are the criteria. XU, that is the depth of neutral axis, is greater than XU max. Epsilon C reached to its ultimate value, so is equal to epsilon CU equal to 0.0035. Epsilon S, at the time of failure, the strain developed in the steel is less than the yield strain, which is given by the formula Fy upon 1.15 ES plus 0.002. Now, though XU is coming greater than XU max, for the design purpose, IS 456 does not permit to take the advantage of XU steel as the failure is brittle. See, though XU is greater than XU max, we never consider a section with the actual value of XU, which is greater than XU max. So we IS code restrict the XU to the XU max value. So even though whatever the XU value we are calculating to define the over reinforced section, suppose your XU max value is, say, let us assume the XU max value is coming as, say, 150 and your XU value is coming as, say, 160. So obviously by comparison of these two values, we are getting the type of a section as over reinforced section. Still, for the further calculation of moment of resistance, we never use the actual XU value. It is always limited to the XU max value. This is because the failure is sudden, the mode of the failure is brittle, and to avoid that, IS 456-2000 limits the value of XU to XU max. So for calculation of ultimate moment of resistance, we have to consider XU max in the calculation and not XU for over reinforced section. Okay, so the formula for MUR max or MUR for over reinforced section is given as 0.36 FCK B XU max into bracket D minus 0.42 XU max, or in other terms it is RU max into BD square. So this is the only formula which we can use to calculate the moment of resistance for over reinforced section. We cannot use the second formula, that is TU into ZU. That formula is not applicable for over reinforced section. So can you think for a while and can you give me the reason why we cannot use the second formula for calculation of moment of resistance for over reinforced section? Just I will give you a 1 minute time to think over this and tell me the answer.
And which formula?
The second formula, mu equal to TU into ZU. That formula, that is 0.87 FY AST into bracket D minus 0.42 XU max. That formula, why we cannot use for over reinforced section? Or can we use it?
Ma'am, if we will use it, it will give us the excess advantage of the steel and we will get more strength of our structure, and therefore it is not advisable to use it.
Correct. It will not give the true value of moment of resistance, because what is the formula? I will go back for the under reinforced section. 0.87 FY AST into bracket D minus 0.42 XU. Even though in place of XU I'm putting XU max, I don't have the exact value of FY at the time of failure. See, in case of under reinforced section, at the time of failure, the steel has already crossed its yielding. So we have a value of FY as 250 or 415, whatever is the grade of the steel we have used. And concrete also has reached to its maximum strain. So FCK value also we know. So both these formulas or either of these formulas are applicable for under reinforced section. This does not happen in case of over reinforced section, because in case of over reinforced section, the failure is because of the failure of concrete first. The strain developed in the steel is not equal to the strain corresponding to yielding, and hence the stress is also not equal to corresponding to the yielding, that is Fy value. So we can use that formula 0.87 Fy, but at the time of failure, whatever is the stress in the steel, that we must know, and that will be obviously less than the Fy value. That is, either if we are using mild steel, then the Fy is 250. So the stress in the steel at the time of failure in case of over reinforced section will be less than 250, or it will be less than 415 depending upon the grade of the steel. We must identify that value first. We must find out that value and then we can use that formula. So it doesn't mean that we cannot use that formula. Only the condition is that corresponding stress in the steel must be known at the time of failure, which is less than the Fy value. Is it clear?
Yes, ma'am.
Okay. So I hope you have written these formulas for over reinforced section.
Yes, ma'am. Done.
Okay. Okay. All right. So this is about the singly reinforced sections. Balance section we have seen in last week. Today we have completed under reinforced and over reinforced section. Let us solve now some numerical examples. You just note down this example in your notebook. What is the description? I am just reading that. A rectangular reinforced concrete beam has a width of 200 mm and effective depth of 400 mm. Calculate ultimate moment of resistance of the section if it is reinforced with 2 bars of 20 mm diameter, and the second case 4 bars of 20 mm diameter. Take M20 grade of concrete and Fe415 grade HYST reinforcing steel. So just note down these values. Once you finish your writing, please let me know.
Done, ma'am.
Everybody has written?
No, ma'am.
Come on, write it fast.
Done.
Girls? Okay, all right. So I will move to the whiteboard now. Okay, what is the given data? I'm just going to write down it over here.
Uh, Width is 200 mm.
Okay, and
Depth is 400 mm.
okay, so I will quickly draw a cross section here. All of you are requested to draw the diagram. So this is a cross section of a beam. This is the neutral axis. And what is the width of the beam?
200 mm.
So this is 200 mm. Effective depth, for that I have to show the reinforcing steel first in the tension zone. Let us consider first case here. So I will simply write down here, we will solve first A. So as per the given data for first case, how many bars are there?
2 bars of 20 mm diameter.
Okay, of 20 mm diameter. So these are the 2 bars which I have drawn here. Let us fill it because it's a solid bar. So these are the 2 bars of 20 mm diameters. Now I can show the effective depth here. Which will be up to the center line of
Bars.
yes. What is the value of effective depth?
400 mm.
400.
400. Okay, 400 mm. All right. What else data is given? That it is mentioned that the M20 grade concrete is given, and um, what is the grade of the steel?
Fe41.
Fe415.
Yes, Fe415. So based on this data, I can write down that FCK value is given, which is 20, Newton per mm square, and Fy value is also given, which is 415 Newton per mm square. Okay. Now the details of reinforcing steel is also given, that there are two bars of 20 mm diameter. So I can find out the area of the steel, total area of the steel. It is simply area of the circle. How we calculate area of a circle?
Pi by 4 d
5
square.
by 4 d square.
Pi by 4d square.
Pi by 4 d square. D is the diameter, which is given as 20 square, and such two bars are there. So this is my AST. Tell me the value.
628.32
628.32 unit
mm square.
mm square. Do not forget to write down unit. Huh? Okay, now the first step, we have to find out the type of the section. Okay, for that we
Ma'am,
have to calculate. Yes.
ma'am, why we have multiplied with 2? We are taking both sides or for both rod.
There are two bars now. So pi d square by 4, it is giving me the cross-sectional area of a single bar. So we have two bars.
Yes, ma'am.
All right. Okay, now to find out the type of the given beam, we have to first find out the XU value. Okay, so tell me the formula of XU for under reinforced or even over reinforced section. In general, the formula of XU.
0.87.
Yes.
AST FY
Okay, FYAST.
Divide by 0.36 FCK
0.36 FCK
into B.
into B. Okay. So simply put all the values now in this formula and calculate XU. Okay, so it is 0.87 into FY value is 415 into AST is 628.32 divided by 0.36 into FCK is 20 into, what is the B value? It is 200. 200. So what is my XU value coming?
15.75 into 10 raised to 3.
15.75 unit?
107.54.
157.
157.54.
Mm.
157.54.
54 mm. Okay. Now we have to compare this XU value with XU max. XU max is given as KU max into D. Okay, so you need to find out first KU max. So every time, though we have filled a table in the last week that for given grade of a concrete and grade of the steel, how we can find out KU max, we already know. But instead of that, there is one shortest way to find out XU max or KU max. For that, you need to open your IS code now. Okay, so all of you just open IS 456 and let us go to section 5 over there. That is page number 67. Everybody, I hope, is having code with you right now. Have you opened it?
Yes, ma'am.
Okay. So go to page number 69. Okay, 70. Page number 70. You have a figure of stress strain curve for mild steel, figure 23. Below that, you'll find out one table or a note. Have you got this note?
Yes, ma'am.
The limiting values of the depth of neutral axis for different grades of steel based on the assumption in 38.1 are as follows. So for different grades of steel, the XU max upon D, that is your KU max values, are already given in the code. If you have the table which we have prepared in last week, just compare the values of those tables for the different grades of steel. It is the same, right? For 250 we have calculated, it was 0.53. For 415 we have calculated it, it was 0.48. 500 we haven't calculated it last week, but the value is 0.46. Okay, so these values are already given. Ku max values are already given, or xu max upon d value are already given. You can directly take these values for the further calculation. Is it clear?
Yes, ma'am.
Okay, now what is given? There is one more sentence written below this table or this small table. The expression for obtaining the moments of resistance for rectangular and T sections based on the assumptions of 38.1 are given in Annex G. So whatever the formula right now we have derived just 5 minutes earlier for under reinforced section, what is the XU value or what is the MUR expression, all these are given in Annex G. So let us go to Annex G now in your code. Tell me where we are getting Annex G, page number. Yes, what is the page number? Guys, are you looking into your code?
Ma'am, 96.
Yes, page number 96, Annex G, moments of resistance for rectangular and T section. So just check the clause G 1.1, sections without compression reinforcement. Now, as I defined, singly reinforced section, the section in which there is a steel provided in a tension zone only. That reinforcement is called as tension reinforcement. And if you are providing the reinforcement in a compression zone, the reinforcement is called as compression reinforcement. So the section which is without compression reinforcement, that is the steel only in tension zone, it is singly reinforced. For singly reinforced section, the formulas are given already here. See here, XU upon D is equal to, that is your KU, 0.87 FYAST upon 0.36 FCKBD, or I will cancel the D from both the sides, I will get the expression for XU. Okay. Similarly, if the value of XU by D is less than the limiting value, or the KU value is less than KU max, or in other terms, XU value is less than XU max, the moment of resistance formula is given by this formula. Okay, now we have discussed both the formulas for MUR, that is for under reinforced section. Okay, so MU, they have given only the TU into ZU, that expression, but we can use CU into ZU expression also. But if you feel the calculation of MU by this formula, you can use this formula always. This is for under reinforced section. Now for over reinforced, that is if the value of KU by D, that is XU by D, that is your KU value, is equal to the limiting value. KU is equal to KU max, or XU is equal to XU max. That is for over reinforced section. The moment of resistance of the section is given by this formula. Okay, so all these formulas are already given in IS code. There is no need to mug up these formulas, but you need to keep in mind how we are deriving these values. That is necessary. The basic concept behind getting these equations is necessary to understand and keep in mind. No need to mug up the formulas. Is it clear? Everybody?
Yes, ma'am.
Okay.
Yes, ma'am.
So we can use this formula by referring the IS code. We already discussed the formula. So let us go back to our calculation. We have already calculated XU, and now we will calculate XU max. So let us do the calculation for XU max. We have already seen the code for KU max value or for XU max value. So I will simply write down here XU max, which is equal to, yes, I will go back to the code again and
KU max into D.
fine, but I want the value
0.48.
0.48 for FY
0.48.
415. Yes,
415.
correct. So for FY 415, the value is 0.48. So I will simply write down this value over here now. It is 0.48
48.
into D,
Yes.
right? D is 400. So tell me the value.
400. 192 mm.
sorry,
192.
192 mm.
192 mm. Okay. Now compare the value of XU and XU max. My XU is coming less than
Less than
XU
XU.
max. So what is the type of the section?
Under
Under
reinforced.
rent.
Under
Yes.
reinforced.
Therefore, the section is under reinforced. I hope you understand my handwriting. Okay. So for under reinforced section, now how we calculate the moment of resistance? The formula of MUR. What is the formula? We can use any formula, right? So some of the students of the class can use the first formula, that is 0.36 FCKB into XU into bracket 1 minus 0.42 XU, and the another students can use the second formula, that is 0.87. I am using this formula because it gives me the easy calculation. 0.8, even the first formula is also easy. So what is the formula? 0.87 Fy into AST. Yes.
Into bracket
D minus
42
0.42 XU.
XU.
Okay. Right. So let us put the values here. 0.87 into Fy is 415 into AST. Okay. So what was the AST value? 628.32. 628.32 into bracket. What is the D value? 400, right?
400. Yes, ma'am.
400 minus 0.42 into XU. Now, what is the XU value? The actual XU
157.
value. 1.
157.54.
Correct. So let us find out the MUR.
75.73.
72.45 mega.
Again, 75 point.
73.
72.
6.
72.4.
I'm 75.
75.73
73.
unit.
Into 10 raised to 6.
Okay, into 10 raised to 6 unit.
Mm raised to 4.
Yes, mama.
Its movement,
Newton mm.
Newton mm.
Newton-
Okay, so
Newton mm.
instead of writing into 10 raised to 6 Newton mm, I am simply write down kilonewton meter. Correct?
Yes.
So this is my final answer. For the first A part or A case, I'm getting the MUR value as 75.73 kilonewton meter. Now in the same fashion, you can solve a B part also. So all of you just start solving the next part. I'm not going to write now all the steps here. I will simply write down for case number 2, the AST value is different because number of bars and the diameter are something different. Okay. So can you just tell me the values over there? How many bars are there and
4 bars.
4 bars. Okay.
20
So
mm diameter.
4 bars of 20 mm diameter. For that, your AST value will be something different. So just tell me after calculation, what is the AST value you are getting?
1256.63.
1200.
56.
Okay, 1256.63.
63.
Okay, mm square. All right. So the remaining steps will remain same. Find out XU now. I'm directly writing XU value once you do the calculation and tell me the value.
315.07.
315.07
07 mm.
mm. Correct. XU max value. Will it remain same?
Same.
192.
Yes, ma'am.
Yes.
Yes.
For the earlier case, we have already found 192 point or 192 only. What was XU max? 192. Okay. So for 192 mm, compare XU with XU max.
Under reinforced.
Over enforce. Over enforce.
Over reinforced.
So now your XU is coming greater than XU max. So the section is over reinforced. Write down in your notebook. The section is over reinforced. So for over reinforced section, how you calculate MUR?
0.36 FCK into B into XU max into D minus 0.42 XU max.
Correct? Is it correct, whatever I have written?
Yes, ma'am.
Okay. So find out now.
Ma'am, D minus 0.42.
Bracket मध्ये D minus
Yes,
0.42.
yes, correct. D minus. Tell me now MUR value.
88.30.
88.29 in
88.29. Unit is important, guys.
Kilonewton meter.
Correct. Kilonewton meter. Okay, now if you observe the two MUR value, in the first case, there were two bars of 20 mm diameter. So MUR value is around 75 something, right? And for second case, we have increased two more bars. So the MUR value has been increased, 88.29. Is it clear how to find out the type of a section, and for that corresponding type of a section, the moment of resistance of the section?
Yes, ma'am.
Okay.
Yes, ma'am.
Now we will see one more problem today. How much time is left now? Yeah. Let us see the next problem. Just note down this problem. Over. Have you noted down the problem statement? Guys,
Yes, ma'am.
Okay. So I'm just reading the problem statement. Calculate the working UDL excluding its weight. Sorry, excluding, there is a typo mistake. Excluding self-weight. Okay. So calculate the working UDL excluding self-weight by LSM for the beam detailed as follows. Clear span is equal to 5 meter. Width of support is 300 mm. Width of beam is 300 mm. Overall depth of beam is 500 mm. 4 number of 16 mm diameter bars on tension side. So it is a singly reinforced beam. Clear cover 35 mm and materials used are M20 and Fe415. So let us start solving now the problem. Okay, tell me now what is the given data. Students,
Unclear span 5 meter.
let us draw the cross section of the beam first. Okay, so what is the width of the beam given?
300.
300 mm. Okay. Okay, let us draw the neutral axis. And how many bars?
4 bars of 16 mm dia.
Okay, so 1, 2, 3, and 4. I have drawn a very small circles over here. Okay, all the 4 circles should be of same dimension. And they have not given the effective depth here, they have given the overall depth. Okay, so what is the overall depth here?
500.
500 mm. Overall depth is given. We have to find out the effective depth. Okay, so overall depth is denoted as capital D, which is given as 500 mm. We have to find out the effective depth. Now the effective depth is calculated as the distance from extreme compression fiber to the CG of the reinforcement. Okay, for that they have given a clear cover value. What is that value? Clear cover.
35 mm.
Sorry, again.
35.
35 mm. Okay, now this clear cover is actually this distance. Okay, this is the clear cover which is denoted by C. Okay, so how to find out now the effective depth?
D minus C.
Overall depth minus cover.
Cover is 35 na? It is clear cover. I want to find out the effective depth at the CG of the steel. Sorry.
Ma'am, also minus the half diameter of bar.
Correct. So I have to consider the half the diameter of the bar. So D, small d will be capital D minus cover C minus half the diameter. Okay. So it is 500 minus 35 minus, what is the diameter of the bar?
16.
Yeah, it is 16 mm bar.
457.
16 by
457.
457. 457 mm.
Okay, I can't write over here. I will write down D over here, huh? 457. That's it.
Mm.
Mm.
There is nothing point, right? 457 point something ऐसा कुछ नहीं है ना? It is simply 457.
Yes, ma'am.
Okay, so this value I have written over here. All right, we have calculated now small d. We have B value, we have D value. We can easily identify now what is the type of the section. We can find out MUR. But to find out the MUR, we don't have Actually, we are not expected, or we are not asked to calculate MUR. What is we are expected to calculate?
Working load.
It is the working load excluding the self weight.
UDL.
And that too a UDL. So we have to find out the working load in the, that is the W, that what is the load acting on the beam. All right. Now for that, let me draw first the diagram of a beam. I will simply draw a line diagram. This is my beam, which is supported on a support. Let us consider this is my column. Okay, and simply a beam is like this. Okay, and this is the second column. And let us assume that the beam is subjected to UDL, which I'm representing here as W kilonewton per meter. The span of the beam is given. What is that?
5 meter.
5 meter. Okay. Now this span is given as a clear span. Now clear span is nothing but the clear spacing between the two columns. So this is the distance. But actually when we represent a beam and its reaction, the same beam, if I want to represent in the form of a line diagram, this is my beam and these are the reactions. These reactions are always calculated at the center of the support. So my reactions are coming somewhere over here and here. Okay. And when I calculate this distance between the two reaction points, it is called as effective span. Now, obviously, if you know what is the width of the support, so half from this support and half from this support, addition to the clear span, it will give me the effective span. Okay, so I can write down here effective span. Sorry.
Hello.
Yes.
मॅम काहीच ऐकू आलं नाही मधलं, ब्रेक होत होतं voice.
Okay. Am I audible now clearly?
Yes, ma'am.
Okay. Have you understood this diagram? This is a beam which is resting on two columns. Hello? Am I audible?
Yes, ma'am.
Okay.
Yes.
So the 5 meter span is given as a clear span. Clear span is the distance, clear distance between the two supports of the beam. So if this is column number 1 and this is column number 2 of supporting to this particular beam, the clear distance between these two columns is 5 meter. In the calculation, that is when we calculate the moment, the shear force acting on a beam, we need to consider the effective span for the calculation. And the effective span is represented as the center to center distance between the reactions. Okay, so the same beam I have drawn here as a line diagram. So this is a entire beam and two reactions are shown here. These reactions we always show at the center of the column. Okay, so these two reactions I have shown here. I hope you have understood this. Otherwise, I will change you the color of the pencil. So I can draw this with a red color. Okay, so this is at the center of the column. Now the width of the column or the width of the support is also given. So the effective span is, now we can calculate as effective span, which is denoted as L effective. It will be clear span plus the distance of the center of the width. Half the width of the support, right? So now in this direction, or if this is the first column, the half the width of the support is, what is the total width of the support given?
300
mm.
300. So half of 300 of the first support and half of the 300 of the second support. I will write down clearly 300 by 2 plus 300 by 2. Oh, limit is over. Okay. So my effective length is coming as, yes,
5.3 mm.
5,300
5,000.
5,300 mm.
So what mistake I have made here? This should be in meter, right? So it is 0.3 by 2 plus 0.3 by 2.
800.
Can we calculate it?
Yes, what is the value?
5.3 meter.
Correct. This is the effective length. Now this effective length value we have to use for the expression of bending moment, because we want to calculate the load, right? And for calculation of load, we must know what is the moment acting in the beam. So let us find out first the moment of resistance given by the beam. So for this beam now, to calculate MUR, we need to first calculate what is the depth of neutral axis. So let us find out XU first. Quickly find out XU for the given data. The
Ma'am,
expression is,
without AST.
yes, calculate AST, correct. So first calculate AST. So there are 4 bars of 16 mm diameter. So pi by 4 into d square multiplied by 4 bars. Tell me the value.
804.
804.24 mm square.
Correct. Now find out XU.
134.43 mm.
134.43 mm.
43.
Everybody is getting the same value?
Yes, ma'am.
Yes, ma'am.
So for the given data of a material, tell me what is XU max?
288 mm.
288 mm. Okay, what is FY value?
Wrong. Management.
What is FY value?
219.36. XU max.
XU max is
219.36.
219.36. Okay. What is the FY value? I have not written here. FY value
415.
415 ampere.
415. Okay. All right. So what is the type of a section you are getting? XU is coming less than XU max.
Under reinforced.
So it is under reinforced. Okay. Now for under reinforced section, we know how to calculate MUR. The expression for MUR, we already know it. Okay. So let us find out MUR first. So MUR is equal to 0.87 FY. I'm directly writing the values 415 into AST. Tell me the value of AST.
804.24.
Into
D. Into
D
4,
is
457.
what is that? 457.
Minus 0.42.
No. Wait. This is in bracket, na? 457. Minus 0.42. XU is
134.43. That comes 116.30 kilonewton meter.
kilonewton meter. All are getting the same value, 116.30.
Yes.
Okay. Now we want to find out
Yes,
the
ma'am.
load.
Yes,
Right.
ma'am.
We want to find out the working load. So basically find out the load. This is the MUR, that is the moment of resistance shown by the beam due to the internal forces. For the equilibrium, MUR must be equal to the maximum bending moment developed on the beam, right? The maximum bending moment we calculate by considering the load. Okay, so I will just write down MUR is equal to MU, that is the ultimate bending moment acting on a beam. Now for simply supported beam subjected to UDL, what is the maximum bending moment? Or tell me the expression for maximum bending moment.
WL square by 8.
Correct, correct. So mu is WL square by 8. So simply we have to equate MUR to WL square by 8 to find out what is the W. So let us equate it. WL square, L is the effective value we have to take. The value is 5.3, na? Am I right?
Yes, ma'am.
5.3 square divided by 8 is equal to 116.30. We have taken the unit as kilonewton meter, right? So W value you will get in
33.12
33.12
kilonewton per meter.
kilonewton per meter. Now this W is actually the design load. See, whenever we calculate or when we design any particular beam, we always design it for the design load. And how we obtain the design load? By applying the partial safety factor to the actual load acting on a building or on any particular section. Okay, so to find out the working load, the actual load acting on a particular section is called as working load. So to find out the working load, I have to divide the working load by partial safety factor. Or if I will go back to your code, see here in the code, we already discussed the partial safety factor and the characteristic strength values, right? Here for loads, we calculate the design load by applying a partial safety factor of gamma f to the actual load, characteristic load, or it is also called as a working load. So partial safety factor for say dead load, we already discussed here. For dead load, I'm considering only dead load, it is 1.5. Okay, so how we obtain the design load? It is 1.5 into the characteristic load or working load. I want to find out the working load here. I have FD value. That W value is nothing but your FD now. Simply I have to find out F. So FD upon gamma F. Gamma F is 1.5. Is it clear?
Ma'am, can you repeat, please?
Okay. See, we have already discussed how to calculate the design loads. Whenever we design any beam, any slab, any column, we always design it for design load. Design loads are obtained by applying partial safety factor to the working loads. So this is a formula, FD equal to F into gamma F. Gamma F is your partial safety factor, F is your characteristic load or working load, and FD is the design load. Now, in our calculation, whatever the W value we have calculated, it is the design load. And we want to find out the working load. So to find out the working load, I have to simply find out this F value. So FD upon gamma F, that is whatever the W value I have calculated, divided by the partial safety factor, it will give me the working load. Is it clear up to this?
Yes, ma'am.
Now, what is the partial safety factor? The partial safety factors are already given here, which we have discussed in the very first week lecture. So for dead load and live load, for this particular combination, the dead load and live load corresponding partial safety factors are 1.5. I'm considering only dead load. So for only dead load also the partial safety factor is 1.5. Okay. So here now this is the working load, the design load. To find out the working load, I have to simply divide this value by my partial safety factor of 1.5. So what is the working load?
22.08
22.08
per meter.
kilonewton.
28.08 kilonewton per meter. This is my working load. Now further in the problem statement, it is asked that we want to find out working load excluding self weight. Okay, so from this load, I have to subtract now the self weight to get the working load excluding self weight. Okay, so in the next step, we will write down the working load excluding self weight. Okay, My handwriting is readable, na?
Yes, ma'am.
Okay. So working load excluding self-weight, it will be 22.8 minus, I have to subtract now the self-weight. How to calculate self-weight for the given beam? We have the overall dimensions of the beam. The
Yes, ma'am.
width is
No, 300.
300 mm. Overall depth is
500.
500 mm. So B into capital D, small b into capital D is my overall dimension. Okay. Multiplied by unit weight of reinforced concrete, which is 25
25.
kilonewton. Yes,
Yeah.
kilonewton per meter cube. So it is 0.3 multiplied by 0.5 multiplied by 25. So the working load excluding self-weight is
Ma'am, 18 point.
Ma'am, what we are calculating in that bracket, is that volume or something else?
this is the self-weight. Self-weight. Overall dimension multiplied by unit weight. This is the area, right? Area, cross-sectional area of the section. 0.3 into 0.5. It is in meter square. Multiplied by unit weight is in kilonewton per meter square.
Ma'am, 18.33.
Yeah. So 18.33
33
kilonewton per
meter.
meter. Okay. So this is the final answer. 18.33 is the working load excluding self-weight. Is it clear? So what we have done here in this problem? I will simply repeat again. We have calculated first the moment of resistance here. Okay, for that we have calculated the depth of neutral axis XU, then we compare it with XU max. We found that it is under reinforced section. Then we calculated MUR by using the suitable formula. We equated it to the maximum bending moment WL square by 8 to find out W. This is the design load. Then we calculated working load by applying the partial safety factor. And then we calculated the working load excluding the self-weight. Is it clear to everybody? This particular problem? Yes. All right. So we will stop today. The time is almost over. It's time to next lecture. We will discuss about the moment of resistance calculation for doubly reinforced section. So we'll discuss first what is the concept of doubly reinforced section, where we provide doubly reinforced section, why it is needed, and then how to calculate moment of resistance and some numerical examples. Now I will give you the link for attendance. Everybody is requested to give the attendance through this link also. So I have given you now the link in a chat box. Everybody has to give the attendance. I'm going to keep this link open for next 10 minutes. Everybody has to give the attendance within next 10 minutes. Okay, guys, any doubts in this? Students, any doubts? Are you there in the class? Hello?
Ma'am?
Yes, ma'am.
Ma'am, what
Yes,
was that? What was that 25 that we have multiplied with the breadth and width?
25 is the unit weight of reinforced concrete. You must have learned the concept of unit weight, which is
Yes,
in
yes,
kilonewton per meter cube. So for plain concrete, it is taken as 24, and for reinforced concrete, it is taken as 25. Again, these values you will find out in IS 875 part 1. all the unit weights of the different materials are given in that code. So you can refer that code to find out the values of unit weight for various materials. For RC, reinforced concrete, it is 25. Is it clear?
Ma'am.
Yes, ma'am. Yes, ma'am.
Okay.
Hello, ma'am.
Yes.
Ma'am, unit weight is equals to weight upon volume असतं ना?
Mass upon volume.
हा मॅम मग व्हॉल्यूम आपण मल्टिप्लाय केलं पाहिजे ना युनिट वेटला.
गरज नाहीये कारण वी आर गेटिंग इट इन किलो न्यूटन पर मीटर ना. Unit weight is in kilonewton per meter cube multiplied by area. 0.3 into 0.5 is area, right? Which is in meter square.
येस मॅम.
So it is kilonewton per meter. आणि आधीचा जो आपला W व्हॅल्यू आहे तो किलोन्यूटन पर मीटर मध्येच आहे, UDL मध्ये आहे.
येस मॅम.
हा. So if you divide it by volume, then you will get a point load, kilonewton. Any more doubts?
No, ma'am.
Okay, so shall we stop now today's lecture?
Yes, ma'am.
Okay then. Bye, students.